All right, in this lesson, we're going to talk about the equilibrium constant. We've spent the last couple lessons setting these up. We're going to actually plug in some numbers today, and we're going to interpret those numbers and look at how equilibrium is affected for our reaction. So in this first example, it says calculate the value for the reaction quotient for the following reaction. And then it gives us some values down at the bottom. So when we set this up, it's always products over our reactants. Anytime we have a coefficient, that is going to turn into an exponent. In this case, they're all aqueous, but if we had a species in our reaction that was either solid or liquid, we would exclude those from the quotient. So let's go ahead and set this up. So these are all concentrations. It's going to be products over reactants. So we're going to have our copper. And because there's a coefficient of 2, it's going to be raised to the power of 2. We have lead. No coefficient, so we'll just leave it like that. And then in our denominator, reactants, we have copper plus 2. And it's also raised to a power of 2 because of the coefficient of 2. And then we have lead with a charge of plus 2. Okay. Let's go ahead and plug in our numbers here. So we have copper as 2 molar. We're going to raise that to a power of 2. We have lead, which is 3 molar. And then on the top we have, on the bottom we have copper, which is 4 molar, raised to the power of 2. And then we have our other lead, which is a concentration of 5 molar. Okay, so when we put this in our calculator, we want to be careful. We want to make sure that we're actually doing this as a fraction. So I'm going to enter my numerator and denominator in parentheses. So let's go ahead and do this on the calculator. So I'm going to use parentheses for the top. So, oops, let's try that again. Oops. So we have 2 raised to the power of 2 multiplied by 3. And then we're going to divide that by the denominator, which is 4 raised to a power of 2 times 5. And our answer is 0.15. All of my concentrations had 3 sig figs, so I'm going to write my answer as 0.150. Now, we do not have units for our quotients. We do not have units for our quotients. So we're just going to write it just like that. So what does the equilibrium constant mean? Well, if our equilibrium constant is really, really, really small, like way less than 1, usually 0.001 or smaller, that means that the reaction barely proceeds at all. So super slow and barely happens at all. If our if our equilibrium constant is less than 1, that means the reactants are favored. Okay, so that means that our equation is favoring the reactants. If it's greater than 1, that means that our products are favored. Okay, now if our constant is much, much, much greater than 1, usually 1,000 or more, that means the reaction goes to completion. Okay, it completes the reaction, everything is formed, and everybody's happy. And again, we don't have any units for our reaction quotients or equilibrium expressions. All right. So you can find the value of K or Q. You can find those values for an overall reaction if you know the value for each step of a multi-step reaction. Yeah, this sounds like Hess's law, but the rules are a little bit different. Oh boy, look at what's going on here. So we have a reaction. So for each of these rules that we're going to look at, we're looking at this base reaction right here with this value for our equilibrium constant, and this is how we would set up our reaction. So if we flip our reaction, so we're flipping the products and the reactants in the reaction, we are going to raise our equilibrium constant to a power of -1. Okay, raise it to a power of -1. And if we flip the reaction, we are going to flip our setup for our equilibrium expression here. Okay, we're going to go ahead and flip it. So the denominator becomes the numerator becomes the denominator. If we multiply the reaction by a factor, so in this example, by a factor of 2. So we did 2 times our A, which became 2A. We did 2 times the 2B, which became 4B. 2 times C became 2C. So we distributed that 2 all the way through. We're going to raise our equilibrium constant to a power of 2. It gets a little complicated when we have our expression here. So we have the original expression, okay, that's this one right here, but we're just going to put the whole thing in brackets and we're going to raise it to a power of 2. So that will distribute to each term. So our C became 2, our B became 4, and then our A over here became 2. All right, here's where it gets fun. If we combine the two reactions, we're going to multiply their K values. Okay, so we have two reactions, reaction A and reaction B. So we went ahead and combined them. And just like before when we were doing Hess's law, any terms that exist on both sides we can cancel out. Okay, so the C's went away just like that. And we're pretty much just left over with everything else. So our K values get multiplied. So we had 105. So we did 100 times 5 to get our 500 down here. And then as far as the expressions go, when we combine these two expressions right here, we would end up with our C values like this. But since they're both in the, we've got one in the numerator and one in the denominator, they would cancel out just like they did in our expressions. And then our final setup would look like that. Okay, so not as bad as you thought when you first saw those tables, but yeah, it's kind of like Hess's law. So there you go. That's the equilibrium constant.